Okay, hello again. Now I would like to talk about modular train control system. What does a modular train control system mean? Typically in a train you have safety insurance levels. In a train the highest level is still level 4. That means it's not allowed to have any single fault. That's totally different to all other business. In an aircraft it's allowed to have a real small possibility of a single fault which is undetected. In a train, it's definitely not allowed to have. So you have to definitely to find additional measures to deal with a zero fault acceptance. That's a big difference. So in a train, it's much easier to find a secure safety function because it's safe to stop a train. Compared to an aircraft, it's not so easy to find a safe state of an aircraft. But in a train, you can simply stop normally. The only thing is, it's not allowed to stop inside the train, inside a tunnel, and it's not allowed to stop on a bridge. That's the only thing which is not allowed. All other states are safe in a train. So what are typical functionalities where you need the highest safety level? Typically, it's train control and train protection systems. So if you look on an actual train, the main controller is the heart of a train. To that controller you have additional decentralized I/O, which is controlling the brakes, which are controlling dedicated sensors. This I/O is also controlling the cabinet functionalities for the driver, to have some lamps, some control signals are directly controlled by that I/O. You have typically also driver displays which are connected via Ethernet to the main controller. You have also control about the gear, fuel systems and so on. That interfaces are mainly connected via MVB or on CAN bus. So typically, what are really safety critical functionalities? So you have to control the wheel slip and the sliding of the wheels on the train. You have to control and supervise the speed of a train. So you have also to ensure that you have a clear driving, acceleration, braking, and so on. That is the main functionalities in a train. So why do we need better, safe computers on the train? The governments are driving extremely more safety inside the train. The German government is also driving that. They have a so-called SURF program. Here they're requiring the highest safety level for each refurbishment on a train. But nowadays, no train is capable of doing that. Also in the US, you have a big program, it's called PTC, Positive Train Control. With that system, you can ensure that no crash will happen in the future on trains. So it's also a vital system, which is definitely required for still level 4. You see it all in other emerging countries like China, like Russia, and so on, where you have requirements for safe train control systems. Where's the limitation at the moment? Typically the limitation, as I mentioned, is in the controller unit, because that is normally built with a SIL 1 or SIL 2 level. Also I/O is only built for SIL 1. So it's very limited. Here's the biggest bottleneck at the moment, and you have to deal with additional functionality or you find better solutions. Now I will try to show you how such a solution could look like. So for that functionality, typically you have two different form factors, or mainly two different form factors. In Europe, you see mainly 19-inch technique, and in the US or in Russia, you see conduction cooling. You can see here example of an housing. It's according to the ARR standard. So it's a pure American standard for railways. It's really close by to the avionics space, and so it's easy to replace also a safe computer inside the train. Such a modular system could look like I've shown now. So you have the main controller and you have decentralized I/O. It's necessary to provide the highest safety insurance level. Like I mentioned, you have to withstand all the environmental requirements. You have to provide really good power supplies for the complete voltage level. So in the train, you have to deal with 24 up to 110 volts. Typically, you have to deal with a huge range, a variety of input voltages. So you have to withstand with that. And you need a certifiable solution. So the main heart, as I mentioned, would be a train controller. In that example, we have a safety board, which is built up of 3 Atom CPUs. 2 are computing the safety story, and the third one is doing all of the I/O stuff. For real-world communication, we extended that system with a real-time Ethernet solution. And we have also the possibility to integrate digital inputs, digital outputs, frequency inputs as safe boards. And to have communication with legacy systems, it's possible to extend it with the MVB interface, CAN interface, and so on. As I mentioned, real-time Ethernet. It's really good because it's quite easy to build a ring structure, and so you have a real available system, because if you have a broken line, the system is still running, so it's not a problem to deal with that. So on software architecture level, it's quite easy to do that, or should be quite easy for a customer to do that. As I mentioned, we have 3 CPUs, so it's quite easy to split up the safety thing and the I/O thing. So you have a clear separation. So all safety communication is done in the safe part, and the I/O drivers are done by the I/O processor. Over that, we implemented a black channel communication, and so it's not a problem to deal with different interfaces like a normal real-time Ethernet interface or a CAN bus and so on. So how you can program such a system? You need a safe operating system, that's for sure. You need at least 2 safe CPUs. And that's the main logic functionality to program safety software. You will find different solutions to do that. So you can do it in C, C++, and so on. You can also use Skate or modern things to program that. You can also use PLC-like story to do that. On the I/O level, it's much better to deal with, for example, with some Linux. So it's open, you will find a lot of drivers, and it's quite easy to integrate additional functionality to that, because you're not bound to a very limited functionality of a QNX, for example. So with the I/O concept, you're doing all the things like data logging, communication, additional interfaces like Wi-Fi and so on could be done on such an I/O CPU. Software architecture, it's, in sum, is really easy for customer level, because the main basic is a safe operating system. It's built within QNX. It's also qualified up to SIL 4, so the highest level. There are some services to trigger, for example, in Watchdog to build such a safe system, and the customer is only to provide his safe application to control really and train. To have a safe system, you have also to deal with built-in self-tests, for example. You have to show that the memory is still working all the time. So you have to do some tests and measurements all the time. You have also to ensure that you're booting the right operating system, that you have the right configuration of your system. So you have to do all the things on the system boot. As I mentioned, you need communication. Also, a little part of that communication have to be safe. If you have to deal with 2 CPUs, you have also to ensure that both CPUs are doing the same thing at the same time. So you have to synchronize both CPUs, that you can do calculations on both CPUs at the same time, that you have a safe result and can ensure that the result is correct. And to do the communication, you need a safety communication layer to implement a safe communication channel via a black channel implementation. So to make it more easier for customers, you can provide pre-certified solutions. That means you can show with a TÜV, for example, that your software is done in the right way, your hardware is done in the right way. You will get some certifications for that. You have only to provide the customer a safety manual where you describe the customer have to do a built-in self-test every hour. You have to show that you have exactly that usage model which is certified. And that's the main story, that the customer can save a lot of money. So why it's good for a customer? Because typically on old systems you have really limited performance. Nowadays you can provide high performance with an Intel Atom. You have good I/O performance with real-time Ethernet. So as a summary, for rolling stock equipment, you need really compliant systems. In the meanwhile, you will have a lot of more pressure to provide safe systems. You need SIL4 certifications, and you need free programmable solutions and not limited to PLC programming like in the past.